Dear everybody, this time we want to show you a method for hydraulic calculation of a pump circuit, and this is coming also from the practical experience from an existing plant, and we will show you a method which is easy used for different applications. It is taken from also an Excel tool which is the solver, and I will tell you. What is the problem? A pump is feeding three different machines at different distance, so the users are connected by means of a pipework. The overall flow is known, 180 cubic meter per hour. The pipe diameter length is also known everywhere, and the delta P across each machine at a given flow is also known. Those are data given by the equipment vendors. What is unknown is the pressure downstream the pump, so also its power, and the flow at each machine, Qi. This is a representation of the circuit. So here we have the pump. This is the overall flow. The delta P after the pump is unknown as far as the three flows which are feeding the three users, represented here by three heat exchangers. And downstream heat exchanger, we have also a control valve. We will see afterwards what's the reason for that. And then there is a closed loop, and there is a tank from which the pump is sucking the water. We need to write some equations. The first equations are saying which are the constraints. The sum of the flows through each machine is equal to the total flow. Then we have the second equation, which is saying that the delta P across each user is equal to the delta P of the user behind, which because they are in parallel, plus the delta P across the pipe branches. And this is valid for the equipment number 2 and for the equipment number 3. And then we have another equation, number 4, which is saying the delta P from the pump to the first node is the same as the delta P from the last node and the tank, because the pipeline has the same length, practically the same size, as you can see from the circuit schematic. And finally, there is also a physical law, which is the general law, saying that delta P at a single branch pipe is equal to this function, is a constant divided diameter to 5 times the length plus a constant which is depending upon the equipment. So this is practically the pressure drop across the equipment, and this is the pressure drop over the pipe branch, and this is proportional to the square of the flow. If there is pipe and equipment, we need to use both terms, and we can express this general formula in those three equations, which are referring to our circuit. So for the pipe branch P1, P1 start, P2, P2 start, P3, P3 start, which are the pipe branches across each user with the corresponding flows which are unknown, Q1, Q2, and Q3. If there is only a pipeline, then the second term with the K, it's not taking place. This formula is something simpler. In this case, so we have those expressions for the pipe branches before each user. Finally, we have 10 equations, the 10 unknowns, which are the flows, so three flows, the pressure before and across each exchanger, so there are additionally 6, and the pressure downstream the pump. But the good news that we have to solve only 3 equations. The solving system is definitely made by only 3 unknowns, which are the 3 flows Q1, Q2, and Q3. We can write the second equation by replacing the formulas that we have seen, and all the terms inside the brackets are known. the only unknown variables are the flows, and the same for the equation number 3. Here we see a schematic of the circuit where the pump is always here at the beginning. Then we have the point 1 upstream, the first heat exchanger, the point 1 star downstream, and so on. And here also we represent the known values, the total flow here, the diameter size, the length of the pipe, and the same we are doing also for the remaining branches. For the station 1, 2, and 3 are also known the K values, so there is the hydraulic resistance which is given by the vendor. In this case, we have also estimated the flows, which are gas values, and we will see afterwards how to solve it by means of the Excel tool. The solver will display in the next slide. The first experiment, we put all the regulation valves at 100%, so fully opened. And we write the corresponding equations. We need to write definitely one equation for the main line. It is the pipeline from the pump to the point P1, whose flow is Q0, so the total flow. And in this case, we have only the pipe, so there is no machines in between. For B, we get an experimental value, which is displayed here, and we keep its value constant for all the pipeline, but it's also possible to change it, to make it different for every pipe branch. Then we write the equation for the pipeline P1, P2, and the equation for the pipeline P2 and P3 as displayed here. Then we are starting with the branches where we have our equipment. The heat station number 1, so the heat exchanger, for which we have guessed a Q1 value. It's not important if it's not correct. We put the diameter, we put the pipe length, and the K1. The K1 is the hydraulic resistance of the equipment, which is given by the vendor. In this case, there is only one train, and this value is 12,274 square seconds divided meter to 5. And the delta P is given by the formula where we are adding the resistance of the pipe and the resistance of the equipment. Same for the heat station number 2 and for the heat station number 3. What we need to write as constraint? The constraint number 1 is that the sum of all the flows must be 180. The constraint number 2 is the one we have seen also in the presentation. It says that the delta P across the heat station number 1 is equal to the delta P across the heat station number 2 plus the resistance of the branch pipes P1, P2 and P2 star, P1 star. And similar for the equation number 3, we are saying that the resistance across heat station number 2 is equal to the hydraulic resistance across the heat station number 3 plus the resistance corresponding branch pipes. And the final condition saying that all those three equations should be matched. And we are using now the Excel solver. The solver says that the functions f1 square plus f2 square plus f3 square must be 0. It can be also written as sum product among the three functions. Objective cell is the function f, which must be put to minimum, hopefully to 0. And the variable cells to be looked for are the three flows Q1, Q2, and Q3. Here we have only the gas values, so not the correct ones. Solution has been found, all the conditions are satisfied, and the objective cell is set to 0. Eventually, those are the searched flows, 51, 67, and 62 respectively for the three flows Q1, Q2 and Q3. And the delta P needed by the pump is 472 meter and the corresponding power 3.3 kilowatt. In the second case, we are doing another trial. It means we set a fixed value for our flows. In this case, all must be equal, so 1/3 of 180, 60 cubic meter each. So we input those values here. And we need to search for which values of the opening of the three valves this condition is met. We guess for all of them now 100%, and we call the solver. The set objective is still the cell H33, so the function f, and the variable cells to be changed are the three opening of the control valves, put now to 100% as a guess value. And they are furthermore subject to the constraint that each one must be non-negative and must be less than 100%. Let's start the solver. The solver found a solution. So the three conditions are met, the F is 0, and the values for the opening valves are respectively 100, 77 and 79%. Under those conditions, we can assure same flow at every user. Thank you very much for attendance and see you again.